And welcome. Can everyone hear me?
You stand there and it's louder.
If I stand here, but then I can't write very easily. Okay, so I thought to start off with, we're going to cover some of the very basic material that you should be familiar with in the form of things like divisibility and greatest common divisors, Bayes' lemma, and a whole bunch of these things are important ingredients in the proof of the fundamental theorem of arithmetic, so that will be the setting that I introduce all of those things. A lot of you are already familiar with this theorem, hopefully, because you taught it not very well in high school. In grade 8 or so, you were told that every number can be written as a product of prime factors, and the question never arises of, wait, what if I could do this in more than one way? The actual interesting content of the theorem is that there is only one way to do this, and this is actually not automatically true. There is some content to that theorem, because it's not true in there are sets of things that behave a lot like you think numbers should, where this isn't actually true. And in the 1800s until about the 1940s or so, it was a major part of research. Mathematics was investigating generalizations to the notion of unique factorization. And there was an early attempted proof of Fermat's last theorem that sort of relied implicitly on the fact that the things they were considering have this unique factorization property when they didn't. And then people tried to rescue it and they couldn't. And then lots of fun. Anyway, they coincidentally, not knowing that this was my vague plan, there was someone in this room requested that I talk about unique factorization domains other than the integers and how they can be used in solving problems. And it just happened to be more or less exactly what I was going to talk about anyway, just completely not what I was going to talk about. But I will now, for the sake of we'll look at some of these more general notions of natural numbers where unique factorization actually does work, like the Gaussian integers and Eisenstein integers and polynomials. A lot of things that are true for natural numbers are also true for polynomials. And also, in some cases, you've already seen those theorems. They haven't been called that. Turns out if you've ever done partial fractions in your life, that's the same thing as Bayes' lemma, but for polynomials. If you've ever done the branch interpolation in your life, that's the Chinese remainder theorem, but for polynomials. If you've ever done, and so on, there's a list. Anyway, to the start. Also, a general philosophy or approach to a lot of problems is prime numbers have very nice properties. They're much easier to deal with than numbers in general. And it's often a viable tactic to think of the numbers in terms of their prime factors. Try to figure out what prime factors they can have. Try to solve the problem for prime numbers first, and then use sometimes something like the Chinese remainder theorem to get that it holds for numbers in general. But prime factors, primes are important. Primes are, when in doubt, consider primes. Yes, if you've got a full list of primes that could possibly divide a number, you have a very rigid grasp on what that number can be. So the fundamental theorem of arithmetic, fundamental theorem, let's write it out. Fundamental arithmetic is that every natural number n can be written as a product of prime numbers with some exponent. And that there's only one way of doing this, where we consider two ways of doing this the same if they use the same prime numbers to the same exponents. In other words, if we just reorder the factors, we consider it. We don't consider 2 times 3 and 3 times 2 to be two different factorizations of 6. These are considered to be the same thing because they both use 2 once and they both use 3 once. And the obvious, I shouldn't use the word obvious, but the easier part of the theorem is that you always can break it down, because the proof essentially goes, well, either my number's already prime, in which case it is its own factorization. Otherwise, it's not prime, so it has two smaller factors, and then by induction, those can each be written as a product of prime powers, and so the existence is more straightforward. The fact that it's unique is the actually interesting. Yes, you have a question?
Is it possible that in some number system you would have like a loop?
Yes, actually, thank you for bringing that up. I was saying that this is intuitive and like the easier part of the theorem, but even here there are some hidden assumptions that we are working with, and that's that we can actually break this number up into, once we pick off one of the prime divisors, in the integers we always get a smaller number that we can then repeat this process on, and then take another prime divisor and repeat the process, and then take another prime divisor and repeat the process. But in principle, it could be weird number systems where these sizes don't behave nicely when you take off. I can't think of any examples offhand. Negative numbers are how they're related fundamentally. When you're talking more generally in rings in general, when we talk about unique factorization, this uniqueness property is also only up to something called units, and units are any numbers that are a factor of 1. In the integers, the only factors of 1 are 1 and minus 1. But in some other number systems, there are other numbers that are factors of 1. So for example, in this number system, this number, square root 2 minus 1, is a factor of 1, because square root 2 minus 1 square root 2 plus 1 is equal to 1. So this is something that divides 1, and that, if we consider numbers that look like a plus b times square root 2, then it's no longer true that the only numbers that divide 1 are 1 and minus 1. And those, if you want to talk about, I don't think this is a unique factorization domain. Don't quote me. Is it? Okay, apparently, according to Jean, this is a unique factorization domain. Don't quote me. But in those cases, when you talk about unique factorization, it's up to reordering these things, and some of the primes, they're no longer necessarily equal, but they might differ by a unit. So in general, P1, A1, P2, A2, P, K, A, K is considered to be the same as Q1, B1, Q2, B2. This is a very awkward way of writing it. If there's some permutation sigma of the numbers from 1 to k, and there's some set of units, epsilon 1 up to epsilon k, such that pi is equal to q sigma I times epsilon I for each I. I'm not going to write that down, but if the primes are let's write that down. If there is a permutation sigma of k and units such that pi is equal to epsilon I q sigma I for each I. At least in the integers, we're also going to consider these things to be the same factorizations as minus 3 times minus 2. And we're also going to consider that to be the same factorization as minus 2 times minus 3. The minus 1 is now a unit, and this is now not the same prime as this, but the same sort of equivalence class of primes, where we consider them equivalent if one divides the other. And so in this unique factorization domain, you get some very bizarre things that are actually the same factorization. So 6 is equal to 2 times 3 is equal to 2 square root 2 minus 2 3 square root 2 plus 3 are the same factorization as far as when you're talking about what a unique factorization is. Anyway, why is this true? Why are these factorizations unique? The key lemma or theorem that allows you to prove this thing is called Euclid's lemma. And what it says is that if A divides B times C, and A and B are relatively prime, then A divides C. One, then A divides C.
GCD-AB1, that's relatively prime.
Yeah, that's relatively prime. A comma B are relatively prime. Or we say that they are relatively prime if they have no factors in common other than 1 and minus 1 and whatever the units are in the thing that we're considering, but in the integers of 1. 1 is the greatest common divisor. In particular, if A is a prime, so I'm going to say if P is a prime, if P is prime, and P divides AB, then P divides A or P divides B. Because if P does not divide A, then P and A have got no factors in common. Because the only factors P has is 1 and P. So the only factors they could have in common are 1 and P. So if they don't have P as a common factor, i.e. if P does not divide A, then their greatest common divisor is 1. And so this tells us that P divides B. And then by induction, you can get that if P divides any product of numbers, then it divides one of the things in the product. So if it divides A, B, C, then it divides A or B or C. As a side note for anyone that wants to go read any honors university course notes on algebraic number theory for some reason, because that is properly where talk of unique factorization domains belongs. This property, that if a P is a number such that whenever P divides AB, then P divides A or P divides B, is used as the definition for what we mean by a prime number. And the concept that you're more used to calling as prime number, that the number is prime if its only factors are 1 in itself, that's usually called the irreducible number. And in the integers, they're the same thing. And in fact, in any unique factorization domain, those are the same thing. That isn't, yes, it is. But in general, those are not the same thing. Not being able to be split apart and having this property is actually something that's special to the integers and is a consequence and implies the fact that the integers are UFT. So why does this imply the fundamental theorem? Well, we have that if P1 to the A1, P2 to the A2, Pk to the AK is equal to Q1 to the B1, Q2 to the B2, Qm to the Bm. So we have two different factorizations of the same number. What we know is that means that P1 divides n. And so P1 must divide one of these prime numbers. Divides n, so divides Qi for some I. In the integers, this means that P1 must be equal to Qi, and then we cancel that factor and we get a smaller number that has got two different prime factorizations, and then again one of those primes must divide one of the remaining primes, and you cancel those factors and you get an even smaller number that has a, yeah.
Why does this group not generalize to unique factorization domains?
It's this property here that's actually the, if you've got Okay, so here's the thing. When we prove that this factorization exists, before we spoke about uniqueness, the property of primes that we were using was the irreducibility. Because we said either a number is prime, in which case it is its own factorization, or it's reducible. It can be broken apart as two factors. And then we can repeat the process on those two factors. So the fact that this exists relies on, you can, in every ring, let's use words you don't know, in every ring you can take any element and you can write it as a product of every, not in any ring, in rings with sufficiently nicely behaved, because as he said, you might have these weird, in sufficiently nicely behaved rings, you can always write a number as a product of irreducible elements. I think Noetherian ring is, whatever, word, doesn't matter. Sufficiently nicely, you can always do this. You can always write it as a product of irreducible elements. Over here, however, to prove the uniqueness, we're relying on this other property that primes have, that if it divides a product of some elements, then it divides one of the elements. The fact that those two notions of prime are the same thing is something that's special in UFDs and is not true in non-UFDs in general. So our main goal then is to, hopefully you can see how to fill in the details of the sketch of that proof. So our main goal is now to prove that this thing is true, and this thing follows from another theorem that you will hopefully know, which is called Bézi's lemma. Which says that if m and n are natural numbers, integers in general, if m and n are integers, then there exist integers s and t such that s times m plus t times n is equal to the GCD of m and n. So the greatest common divisor of any two natural numbers can always be expressed as a linear combination of those two numbers that you're interested in. In fact, this is the smallest number that can be written in this way, because we know that anything that divides m and n has to divide anything that looks like this. So every number that can be written in this form is divisible by the GCD. And the fact that the GCD can be written in this way means that every multiple of the GCD can be written in this way. That's exactly the set of numbers that can be written in this way. Before I prove this, let's just see how this... I'm doing this very backwards. I should have started at Euclid's algorithm, said, hey, look, Bézi's lemma is a nice consequence of that. Hey, look, Euclid's lemma is a nice consequence of that. Let's prove fundamental theorem, but whatever, we can do the lecture backwards. Maybe start writing at the bottom of your page and then move upwards. Or take the pictures. Actually, no one writes lecture notes anymore. I've been in enough classes where people just sit and like idly stare at the lecturer for 45 minutes, then take out their phone and take pictures of the whiteboard, and then that's their notes for the course. And I fully expect you to do the same. So when you take out your phones later and photograph these boards, start here and go that way. Cool. Okay, why does this imply this? Well, let's suppose that A divides... Okay, so let's go Bézi implies Euclid. I think actually, I'm not sure if Euclid had this more general version. He might have just had the prime version. But sometimes I think this one's called Euclid's lemma. Sometimes this one's called Euclid's lemma. Whatever. Bézi implies Euclid. So let's suppose A divides BC. A divides BC. And GCD AB is 1. Then there exists a linear combination of A and B, which is equal to 1. Then there exists S comma T such that AS plus B times T is equal to 1. Now we take this whole thing and we multiply it by C. Then ACS plus BCT is equal to C. And this term is divisible by A because it's got an A in it. This term is divisible by A because BC is divisible by A. Hence their sum is divisible by A. Yes. You have a question? I'll take that as a no.
Can we just, I thought we would, oh wait, BCT is divisible by A.
Yes, because BC is by assumption.
Right.
And the other term's got an A in it, so it's divisible by A.
For a second there, I thought we had gotten stuck in circular logic.
Yeah, okay, that's easy. It's, yeah, so this is divisible by A. This is divisible by A because BC is. And so therefore C is divisible by A. As a very quick side note, the other thing that is a consequence of this that you should also know, or not should, let's go with, if you don't know, now you're going to learn it, but that you might already know, is that it's a related theorem, but it's not the same theorem. If A divides C and B divides C, and the greatest common divisor of A and B is equal to 1, then AB divides C. If we already had the fundamental theorem, these actually become easier to, or not easier, but you can prove these by considering the prime factors and counting how many times they divide the terms. But considering that I'm using this to prove the fundamental theorem, that would be getting trapped in circular logic, and yeah, that's not good. Joel would call me out on it. So if A divides C, then we know that C is equal to something times A, MA, for some M. So then we get that B divides MA because C is equal to MA. This is the proof now. So B divides these two things, and A and B are relatively prime. So this implies then by Euclid's lemma that B divides M. And so, yeah, we get that. Yeah, so AB divides AM, which is equal to C. And that's like a very basic version of the Chinese remainder theorem. It's the uniqueness part, essentially. I have to say the word Chinese remainder theorem at least 4 times a lecture, because that's what's come to be expected of me. Okay. How do we get Bézou's lemma? It's a consequence of Euclid's algorithm for calculating greatest.
What's the name of that lemma?
This one doesn't have a name, it's just something that people do. Now we'll say 3 divides this and 7 divides this, therefore 21 divides this. But it does rely on the fact that A and B are relatively prime. If all you knew was that 2 divides C and 4 divides C, the best you can say is that 4 divides C. You can't say that 8 divides C.
Is that the same as saying that GCD of A and B divided?
It's the lowest common multiple of A and B will always divide C. Yeah. Sometimes that's used as a definition of lowest common multiple is that it's a number that divides every other common multiple. That's not the intuitive definition. The intuitive definition is it's the smallest number that's a common multiple, but then those, it turns out that those two things are the same thing. Just like if you have any two common divisors of, if you have a common divisor of any two integers, then that common divisor will divide the GCD. So it turns out not only is the GCD the largest common divisor, but it's actually a multiple of every other common divisor. So Euclid's algorithm. Oh, I'd just like to say that these four boards, they all have the name Euclid attached to them. Euclid lived sometime in like 300 BC. I promise, though, that we talk about other unique factorization domains since there was a request. That stuff comes around in like the 1900s. So we're going to jump forward 2100 years just now. Euclid's algorithm. Euclid's algorithm is a method for calculating the greatest common divisor of two natural numbers, and it relies on this observation that the GCD of A and B is equal to the GCD of A minus B and B. And therefore, to save ourselves time, if we're actually carrying out this algorithm, it's equal to the GCD by induction of A times any multiple of B and B. And the reason why this is nice is because the remainder when you divide A by B is something that looks like that. So you can replace A not with A minus B, but with the remainder where you A minus A by B, and you get a much smaller number involved. So why is this true? This is true because the numbers that divide both of these, the common divisors of these two numbers, are exactly the same as the common divisors of these two numbers. Not just the greatest ones are equal, all of the common divisors are the same. And so in particular, the greatest one is the same. So this is true because if D divides A and D divides B, then D divides A minus B, and so every number that's a common divisor of A and B is also a common divisor of A minus B and B. On the other hand, if D divides A minus B and D divides B, then D divides the sum of these two things, so it divides A. And so any number that's a common divisor of these two numbers is a common divisor of these two numbers as well. And voila, they have the same common divisors, so the largest one is equal. And then you do this repeatedly. You subtract the smaller number from the larger one repeatedly until you get smaller numbers. And this will eventually stop. You will eventually get to a point where you keep doing this as long as one of the numbers is smaller than the other one and positive. They're both positive. We will assume that they're both positive. And this stops because on each step, the total of the two numbers is getting smaller, so you can't carry on forever. This is also obviously true for the integers, but it is actually fundamentally comes down to it. One of the reasons why the integers is a unique factorization domain is because we have this quantity associated to them that decreases when we use Euclid's algorithm.
Use Euclid's algorithm in any...
You can try to use Euclid's algorithm in any ring you like, but in some rings, there isn't a notion of size where your two numbers are actually getting smaller.
Right.
The rings where you can define a notion of size, where the two numbers are getting smaller, and hence the algorithm eventually terminates, those are called Euclidean domains. And integers is a great example of a Euclidean domain. Polynomials with coefficients in any field is a Euclidean domain. The Gaussian integers is a Euclidean domain, but not every unique factorization domain is a Euclidean domain. This isn't the only way to prove that something is a unique factorization domain, but anything that is a Euclidean domain, i.e. where Euclid's algorithm works. Any domain where Euclid's algorithm works, you automatically get Bayes' lemma. If you have Bayes' lemma, you automatically get that if something's irreducible, then it has this property that if P divides AB, then P divides A or P divides B. And once you have that, you get that if two factorizations are the same, then one of these primes must divide one of these primes, and hence be a unit times this prime. And yeah, so Euclidean domain, if Euclid's algorithm works, your set of numbers, I haven't defined what I even mean by that, but yeah, your set of numbers will be a UFD. And the other way around is not true. Can be a UFD without Euclid's algorithm actually working.
Are you saying Euclid's algorithm will work? You mean the GCDs don't work? Or
And they might still have GCDs, but they just yeah. So more generally, we don't have to. So the argument for why this terminates is that on every step, when we add the two numbers, the larger one of the two numbers is decreasing. And so the larger of the two numbers is eventually going to go down to 0. And so we eventually end up in a situation where we have GCD of something and 0, and then this is the GCD. There's something that's not the 0. Why? Oh, I haven't actually explained why this gives us Bayes' lemma, so let's do that. The key insight here is that at every step of this process, the two numbers involved are a linear combination of the original two. So
that noise when things make sense to me.
Yeah. At every step of the process, we are looking at the GCD of something times A plus something times B, and something else times A plus something else times B. And you can verify that this is true at the start because we're starting with 1 times A plus 0 times B, and 1 times B, 0 times A plus 1 times B. And if you have two numbers that are of this form and you subtract one from the other, you still have something times A plus something times B. So at every step in Euclid's algorithm, the two numbers we have look like this. And so at the end of Euclid's algorithm, when we have a 0 and GCD, that GCD that we have looks like this. I hope that makes sense. And yeah, that's why Euclid's algorithm implies Bayes' lemma, is because if you subtract two linear combinations from each other, it's still a linear combination of the two numbers involved. There's other ways of proving Bayes' lemma, but this is the one I like the most because it's, yeah. It also, I don't know if I actually want to cover that. I have in past years, and it's actually not really useful, is that you can, once you've used Euclid's algorithm to work out what the GCD is, there's a way to go backwards and work out what those coefficients are that gives you. There's a way to work out what one possibility for S and T is. Not the only possibility. These numbers are not unique. In fact, they're very not unique. There's infinitely many that work because you can always just add a multiple of T to M and subtract. You can add T to M and subtract S from N, and it will still have the same value. Okay. And you want some exercises, you can, and these are exercises, they're not, yeah, we can mimic this process, and there are some sequences that have nice properties. It turns out that the GCD of 2 to the n minus 1 and 2 to the n minus 1 is equal to 2 to the GCD of m and n minus 1. And that the GCD of the mth Fibonacci number and the nth Fibonacci number is equal to this Fibonacci number. This one's more complicated to prove because you need a formula for what f m minus n is. Maybe you don't. There might be other ways to do it, but there is a way to prove this, that it's possible to prove that the GCD of Fm and Fn is equal to the GCD of Fm minus n and Fn. And so the subscripts of the indices of the Fibonacci numbers, if you keep track of what they are, you're going to see they're exactly the numbers that appear when you use Euclid's lemma to work out the GCD of M and N. I'll leave you to fill in the details. It's a fun thing to try and to think about. Let's jump forward 2100 years and talk about the Gaussian integers.
Any reference material we can check on?
I can find some and send you. There's lots of books that cover the. I just can't think of any titles offhand. I mean, I can think of a title offhand, but it's the worst possible reference to give you, and that's Euclid's Elements. But there are more modern books that are written on the same topic, and I'll try to find one of them that's nicer. Anyway, jumping forward 2100 years.
On the ring of root 2,
Yeah.
according to IMO compendium, it is a UFP. I don't know if that's reliable enough.
Yeah, that's reliable enough. Finding all the units in that thing is also a fun exercise, because that's the same thing as solving PAL equations, and yeah. Which board can, let's start with this one. Okay, Gaussian integers. Which is Zi. And what this means is that we're looking at numbers of the form a plus b times I, where a and b are integers. And these things form a ring, and what that means, for the first time today, I'll actually say what that means. It means that you can add these things and you still get something of this form, and you can multiply these things and you still get something of this form. And every element has an additive inverse, and there's a zero element that if you add it to anything, leaves everything alone. You don't need to remember that. It's just you can add these things and it's still a Gaussian integer. You can multiply these things and it's still a Gaussian integer. Yeah.
Doesn't it also have to be a multiplicative identity?
Depends who you ask. Some textbooks insist that rings are commutative rings with identities, some textbooks don't. I actually, if you are, in every algebraic geometer will tell you that the only things we're considering are commutative rings with multiplicative identity, but then some people, it's one of those things, is zero a natural number or not? Now, the high school teachers in the room will say no, it's zero is a whole number, but the natural numbers are 1 onwards, and the British will agree with you, and the French will say, are you a moron? Of course, zero is a natural number. And it's not a mathematical question, it's what's the word I'm looking for? Yeah, terminology, but it's semantics. It's a matter of convention. It's not. There's no mathematical substance to that debate. It's just once we've chosen our definitions, we work with them and just make sure that everyone, if you're using a word, everyone you're trying to communicate with understands the same thing by it that you do. So, yeah.
Is this like a vector space as well?
It is a vector. It's not a vector space. It's a Z module, but it's not a vector space because coefficients aren't in the field. But I don't know what they're called, but if you consider Qi instead, you could let these be rational numbers, then that is a vector space over the rational numbers. But this is a Z module, which is like a generalization of a vector space. Where a and b are integers, and to this thing we assign something called the norm of a plus bi is equal to a squared plus b squared. And the norm turns out to be multiplicative, So we have the property that the norm of xy is equal to the norm of x, norm of y. And this norm has got a very important property. It has the property that, you have to, don't quote me on this, but it has the, firstly it has the property that n of x is equal to 0 if and only if x is equal to 0. And it also has the property that, well, okay, it's multiplicative, which also means that, but the important one is that if a and b are if x and y are any Gaussian integers, then there exists a quotient and a remainder. Okay, if x and y are Gaussian integers, then there exists a quotient and a remainder that are also Gaussian integers. Such that x is equal to this quotient times y plus this remainder. So we can do division with the remainder. And this is the important part. And the norm of this remainder is less than the norm of what we're dividing by. And the fact that a norm with this property exists is what makes the Gaussian integers a Euclidean domain, because that means we can use the Euclidean algorithm to calculate GCDs, because we replace, instead of taking a minus b, we take a minus q times b, and then the norm of the larger one of the two numbers is decreasing the whole time.
So can you just go back and define what we mean by norm?
Yeah. So it's defined to be equal to...
Okay, that is just the definition of a norm.
Yeah, so...
Always.
It's another word that's got lots of overloaded meanings.
Yeah.
At least in this context, we just mean something. Often, something with these properties is what we want for Euclid's algorithm to work with this notion of. This is what I meant earlier when I said a notion of size that makes everything work nicely. But this means that this means that if x and y are Gaussian integers, then we have that the GCD of x and y is equal to the GCD of r and y. X minus q, y, and y. And this is equal to r. And the norm of the larger, if we consider the norm of the two numbers involved, the larger one of those two norms is going to decrease, and eventually one of the two norms has to be 0, and at that point the process terminates. And at every step in this process, we still have that the two numbers are a linear combination of the original two. I'm a little bit hesitant because I'm not sure if this is true exactly as stated, but it's close enough to being true to make this work. So also don't, this is definitely true. This is definitely true. I think it's in the, I don't think it's in the Gaussian integers where you have to be more careful, but there is. Exercise check this, and if it doesn't work, let me know and we can figure out what I was supposed to say. So in this case, just taking x minus y might not work, because I don't think it's automatically true that the norm of x minus y is less than or equal to the norm of x, or is less than or equal to the norm of y, but certainly there is a multiple of y we can subtract from x such that the norm decreases, and then we have this whole process, and we have that, then we have Euclid's lemma, then we have unique factorization domain. Here we have to be careful, because here the units are not just 1 and minus 1, but I and minus I are also units. So you don't end up with, no, we don't have that if PQ is equal to RS, where those are all primes, that either P equals R or P equals S. It could be that P is equal to minus R, or I times R, or minus I times R.
Probably a bit slow. The Gaussian integers are of the form a plus br.
Yes.
So they're all like. So when we refer to x and y,
X, I'm just using this as now. X is itself equal to something plus something times I.
yeah. So each of x and y are of the form a plus br.
Yes.
I see.
Yeah. What else did I want to say about this? There was something that just came to mind and I've forgotten what it was. Okay, here's something you can prove using the fact that Gaussian integers are a unique factorization domain. There's lots of things you can prove with this. A proof that I quite like is a proof of something called Fermat's theorem on the sum of two, which primes can be written as a sum of two squares, also called Hughes lemma, which says that, okay, this is also not really what I want to go into today, but some of the integers that are prime numbers are still prime numbers when you consider them as Gaussian integers, and some of them are not. Some of them now have factors. So 3 is still a prime in the Gaussian integers. Turns out you can prove that. But 5 is not, because 5 is equal to 2 plus I times 2 minus I. It's now no longer irreducible, and these are both primes. Anyway, it turns out that it's the primes that are 1 mod 4 that are now no longer primes in the Gaussian integers, and primes that are 3 mod 4 are. Yes.
Is there a reason for that?
There is in fact a reason for this. In fact, I can prove this. In fact, this is part of like.
I wanted to prove that.
Let's prove this. So, if P is congruent to 1 mod 4, then next.
Primes to mean both prime and irreducible things working.
Yeah. So this is UFD. So prime and irreducible mean the same thing. Where prime means if P divides AB, then P divides A or P divides B, and irreducible means only factors are a unit and itself times a unit. If P is 1 mod 4, then and P is a prime in the integers, not in the Gaussian integers. So this is an integer element of Z, and it's a prime. Prime. There exist integers x and y such that P is equal to x squared plus y squared. So for example, 5 is equal to 2 squared plus 1 squared, 13 is equal to 3 squared plus 2 squared, 17 is equal to 4 squared plus 1 squared. Why is this true? So, why is this true? I need to remember the proof now. So, P is... Okay, so this relies on something I haven't proven. We first need to know that there is a number. Let's not call it x because I want to reserve that for the things I find, but I'll fill in let's call it an exercise. Exercise is find a reference for this. If P is 1 mod 4, then minus 1 is a quadratic residue mod P. So exercise if mod 4, then there exists A such that P divides A squared plus 1. That's not obvious, that's far from obvious, let's not call it an exercise. You can construct it explicitly, you can take like P minus 1 over 2 factorial or something like that's supposed to work, yes. Or you can use primitive roots, but that's, I also haven't spoken about it all, or you can, there are numerous ways to do this, but all of them involve stuff that has not been covered in the last 45 minutes, so let's not do that, but accept my word for it, that there's some number a such that p divides a squared plus 1, where p is 114. What this tells us is that then p divides a plus I times a minus I. It divides the product of these two Gaussian integers. But p does not divide this thing, and p does not divide this thing in the Gaussian integers, because what happens if it did? If we have p times a Gaussian integer, s plus t times I, then both of the coefficients that you get are going to be divisible by p. And that's not the case over here, because the coefficient of I is 1, which is not divisible by p. And it's not the case over here, because the coefficient of I is minus 1, which is not divisible by p. So neither of these things is p times a Gaussian integer. So
Why must p divide the coefficients?
well, just take any Gaussian integer and multiply it by p, and what you get? You get ps plus pti. And that doesn't, you know, so if these were p times something, it would look like this. So the coefficient would be divisible by p. So p divides the product of these two numbers, but p does not divide a plus I, and p does not divide a minus I, which means that p is not a prime in the Gaussian integers. P is not, because you'll remember that a prime means that if it divides a product of two things, then it has to divide one of those two factors. So here it divides a product of two things, but it doesn't divide either of the factors. So it's not a prime. Oh, in case anyone forgot to ask and is hopelessly lost because you don't know what I mean by I is the square root of -1, and 20 minutes ago would have been a good time to ask.
Can I also go back a little? When you said subject to x equals qy plus r,
Yes.
q and r being...
Also Gaussian integers.
Oh, they are, I see.
Yeah.
Okay. Fine.
So it's not a prime in the Gaussian integers, and what this means is, because remember, Gaussian integers is a unique factorization domain, so prime and irreducible is the same thing. So this means that we can write p as, so p is equal to x times y for some, let's not use x and y, I still want to reserve, I'm running out of letters. Let's use alpha and beta. Alpha and beta for some Gaussian integers, alpha and beta. And where we can assume that neither of these things are units.
Can you just see a bit further up there?
Those are not units. So now this norm that I defined right at the start and glossed over actually becomes important, because what this tells us is that the norm of p is equal to the norm of alpha times the norm of beta. And the norm of p is equal to p squared by definition, because p is equal to p plus 0i, so its norm is equal to p squared. And so the norm of each of these numbers is 1p or p squared. And exercise, if, in fact, let's do this sensibly. Norm of alpha is equal to 1 if and only if alpha is a unit. And we were assuming these things are not units because p is now not irreducible, so there's a way of factorizing it not involving a unit. So this implies that the norm of alpha equals the norm of beta is equal to p.
How do you know this one? Other factors of p?
This is now in the integers. This norm is a...
Oh, yeah.
This norm a squared plus b squared is a normal integer instead of a Gaussian integer. And if alpha is equal to x plus y times I, then we have that the norm of alpha by definition is x squared plus y squared. And that's exactly what I claimed I was going to prove, that if p is 1 mod 4, modulo this detail that I didn't, as long as you're willing to believe that, and you shouldn't just be willing to believe things, but for now, as long as you're willing to believe that, then you should also be willing to believe that p can be expressed as a sum of two squares. Now, I don't actually have to go this far to prove that p is not a prime. In fact, we already knew that p is not a prime over here already, when p is 1 mod 4. So why are numbers that are 3 mod 4 still prime in the Gaussian integers?
And that is an exclamation mark.
This is an exclamation mark and not a factorial.
Quite dangerous to use.
It is indeed. I wonder what the factorial of a ring is.
Higher also.
Okay, so the other part, I claim that if p is 3 mod 4, then p is then p is a Gaussian prime. The reason why this is true was, suppose it's not, then it's not irreducible, so then it's, suppose not, then p is equal to ab, or alpha beta, where alpha and beta are Gaussian integers, so norm of p, which is p squared, is equal to norm of alpha, norm of beta. Actually, we don't even have to turn this into a proof by contradiction. Just suppose we have a factorization of p, we'll show that one of these factors must be a unit. Yeah, so, no, let's have it as proof, whatever. Sorry, I'm like stumbling over my train of thought now. Mimicking exactly what we had there, this means that alpha can be written as x squared plus y squared. So these are both equal to p if p was a prime. And if p was not a Gaussian prime. And we know then that this alpha equals, norm alpha equals, so p equals. But if anybody that knows that this is true also knows that the only primes that can divide something of the form x squared plus y squared has to be 1 mod 4. So, yeah. That's not a very enlightening proof, I'm sorry. It relies on quadratic residues, which I haven't actually spoken about. So at the end of the week, you'll be able to revisit this proof and say, oh, that's what he meant. Cool. It's actually 5:30 now, so we should actually stop. Unless anyone has any questions or any requests for...
We are going to do quadratic residues later in the week.
I think it's probably helpful to work with.
Okay.
You know, any limited problem where
There was one, there's some horrible thing of like the line to the 5 is equal to x squared plus 1 or something.